Okay, this is number 20 in your book. So let me go ahead and read the problem. So it says, consider an alligator population, P of t, satisfying the extinction explosion equation that we worked on number 18. They give us, so if the initial population is 110 alligators, and there are 11 births per month and 12 deaths per month occurring at time t equals 0, how many months does it take for the population, P of t, to reach 10% of the threshold population? So I have a lot of information down. I wrote a lot of the given information in 18, and so I really hope my pointer works because I'm using it, but it just depends. I don't know, sometimes it works and sometimes it doesn't. But okay, so P of t satisfies this differential equation here, right? So remember this guy we've seen in number 18, and right, beta or B and D, right, were our birth rate and death rate. We also have a ton of initial conditions. We know what P of 0, B of 0, and D of 0 are. Right, from the problem, we're given, right, 110. So let me just maybe underline just in case the pointer's not working, right? We have our 110, 11, and 12. And I derived all of this from number 20. It states 11 births, right, per month, 12 births, 12 deaths per month, and so forth. And I also wanted you to recall this information here on the right. This is from again from number 18. We definitely talked about that. Again, I just rewrote a couple more things from number 18. And so this is, again, a lot of given information. And the goal, right, was to, well, let's go ahead and write, the goal is how many months, right, how many months does it take, that's a does it take, right, for our population, right, of alligators to reach 10% of the threshold population M. So that is 10%, right, of M. So we can definitely, we know what M is from number 18, right? We proved that M was, so we know, so from 18, okay, we know that M, so let me just go ahead and write that down. M is equal to, so D naught, P naught over B naught. And we know these values, right? We know what D naught is. It's 12. My D naught is 110, right? Or we started with 110 alligators. And we're dividing by B naught, which is 11, and if we calculate that, we're going to get 120. So that's our M. Well, if that's our M, well, 10% of 120, right, is just 12. So 10% of 120 is 12. Okay, so we know it's 12, right, when we substitute that 120. So let's go ahead and write that. It's actually very important. So 10%, right, of our, well, let me actually erase that. 10% of 120, we know, is 12. Okay, so now that we found our M, our threshold population, we can definitely move on. So we have a differential equation, and we want to solve for our P of t, right? Because it's asking for how many months does it take for P of t to reach, okay, so in this case, 12. Well, we need a model, and our model is going to be P of t. That is solving the differential equation. And once we find our model, our function of t, then we can definitely solve for t to find out how many months it takes for our alligator population to reach 10% of M. Okay, so this is just letting you know this is going to be a tedious problem, but it's a very good problem. So here we have, so I'm going to go ahead and write some information again. So we have dp dt, our differential equation, and we have ap squared minus p. And again, we want to solve for, right, we want to find the solution of the differential equation, or specifically, right, we want to model first, because this is, I mean, we say question mark, yes, it's going to be a numerical value if we know what t is, but we need our solution. So let's, again, use what we know. So I can say, so dp dt is equal to, again, we can factor out our AP, and then we're left with P minus B over A. And again, I can let M be B over A, right? We know that from 18. And if M is B over A, then we can definitely rewrite this guy, right? We have dp dt equals, right, AP, and then the difference of P and M. Okay, so there's my B over A. And, well, we can, let's try to separate variables, right? You always want to start with separating variables. That's I think, the easiest method to solve a differential equation. And then you move on to, okay, integrating factor. If that doesn't work, maybe let's transform it into a function of v and x and use the substitution method. But, let's see if we can separate the variables. And so separating the variables, we obtain the following. So let's just move that here. So after separating the variables and moving things around, we're going to be left with 1 over p times this quantity, dp of course, is equal to a dt. And if you want to write your dp where that 1 is, right, in the numerator, that's fine as well. And so we separated our variables, so we can definitely integrate both sides. Now the right-hand side is very easy. We just get, right, at maybe plus some constant of integration. But this integral, right, you're actually going to use, so from calculus, you're going to use partial fraction decomposition. So here, remember when you want to do partial fractions, so this is maybe on the side if you'd like. So PF partial fraction decomposition. So PFD, we know, so I'm going to take my function here, my integrand, and I can split this guy up, right? I really want my p here and my p minus m. And I want to find, and I actually, yes, I do want that. Let me get my white here. So I want to find coefficients, right, A and B, such that this is true. And I mean, this is just really some algebra, because it's easy to integrate the right-hand side. So let's see, I'm just going to, I mean, we can definitely, right, combine these fractions. And if we do, right, we get A times this quantity plus B times P. So I'm just adding the fractions right on the here on the right-hand side. And notice, right, we know, I mean, just from arithmetic with fractions, right, if your denominators are the same, then that means that your numerators must be the same. Hence, 1 is equal to A times this quantity plus BP. Now, if you need a review of partial fraction decomposition, you can just peek in your calculus book and you'll see some examples. There were a few examples in the first section. I think, well, in this section 1.7, I want to say 1 through 8. If you'd like me to do one, just please let me know, and I will be happy to do one. We are going to be using it a lot in chapter 2, but I mean, I can do one if you really like. That's no problem. Okay, so here if P is equal to M, then we know 1 is equal to BM, right? Because, I mean, if P is equal to M, then we know this guy is gone. And so we get 1 equals BM. And if we solve for B, all right, that's just 1 over M. Okay, so I have my coefficient B. Now, what if a P is 0, right? And basically we want this quantity to be 0, right? And this quantity to be 0. So now if we want this quantity to be 0, if P is 0, then we obtain the following. We get, let's see, 1 equals A times, okay, negative M. And therefore, if we solve for A, we get the following expressions, right, in terms of M. So we found our A and we found our B. So now we are allowed to, right, plug these guys right in here. And actually, just kidding, a small little error. My A is negative 1 over M. So that should be a negative right there. Okay, so I'm going to stop here because I'm at almost 11.5 minutes. In the next video, we will substitute these values and then integrate and hopefully finish the problem.